some slides on binary star populations. I first want to have a couple of people talk about evolved binaries. I have my own preference for. Wait, is this working? There we go. We've talked about common envelope evolution, but I want to show some actual system post-common envelope binaries, and then we'll come back to our younger binary systems. Ming, Sung, can you talk about your Poseidon population synthesis?
Yeah, yeah, sure. Here I just trying to give a 1 minute introduction of this. Just trying to let you guys know we released a new code just called Poseidon. Like this binary population, this is code I compare with the other fast binary population. This is code this code is based in MESA simulations. So instead of using fitting functions or analytical equation describing the core mass or study the mass transfer history or mass transfer stability. And now our binary population, this is that history is all based on MESA binary evolution. So it's more close to real. And another important thing I would like to mention is that machine learning and active learning is also applied when dealing with interpolation among the final plane of the binary evolutions. We do not do interpolation among different evolutionary tracks, but we do using machine learning in when doing interpolation at the final plane for all the binary tracks. For example, some important parameter like the density or mass, stellar masses, orbital period, something like that. So yeah, so we use machine learning to just interpolate the on the final plane a result. Also active learning is also used in trying to, because we build the binary evolution grid and then doing interpolation among the big grid. And for example, we have three binary evolution grid, double hydrogen rich main sequence stars simultaneously. Is one of the binary grid we work with, and another binary grids are hydrogen rich main sequence star and the compact object, or helium rich main sequence star plus a compact object. Yeah, for those for those big grid, we runs for the original grid contains more than 50,000 binary evolutions, and by using a new active learning algorithm, now the grid can be the number of grid can be reduced to a small number, but we can do a better interpolation result. Just trying to save the computational time. The first version of Poseidon code, dealing with solar metallicity, and we mostly focus on neutron star and binary black hole progenitors. So but in the future, I mean, version of Poseidon, we'll definitely dealing with lower mass and the flow chart here, just trying to yeah. So each square represent a result or initial conditions or the final result. So we start from zero-age main sequence evolution, and yeah, and after one of the star field is Rochelle radius start mass transfer or a common envelope event. For each black dot, that means a event common envelope or stable Rochelle overflow or core collapse supernovae, something like that. And for all the for the event that can be simulated in MESA, we'll rely on MESA simulations. For something else common envelope evolution or supernovae related physics, we'll do on the fly calculation because MESA cannot deal with this event. But maybe because Parbolo is here, in the next version of Poseidon, we will implement the a more advanced version dealing with common envelope event. So yeah, we'll just keep improving that. And could you please go back?
Oh yeah,
to
your
the
collaborators.
first, yeah, just
Yep.
trying to like announce our collaborators. Like we have a big group like in developing the code, and like is so I would like to mention like 2 PIs of this project. Like one is Vicky Kilogra, director of Sierra, and also Tassos Fragos, yeah, he's at University of Geneva. Yeah, so basically this is a collaboration between US and Europe, like, yeah. And also like in our big group, we have like astrophysicists and also computer scientists. Like they are, yeah, help us like dealing with machine learning and interpolation related stuff. I would also like to mention Jeff Andrews in the center of the next, yes.
Yeah.
Jeff is our like core developer, and he's also online. And if you have any questions, like please, Jeff and I will try our best to answer like the Poseidon code question.
Any questions for Megan about binary population synthesis or Poseidon? Andre?
Hi, how much more computationally expensive is this compared to the usual binary population synthesis?
Yeah, because we already like run like nearly, let's see, 100,000 of binary evolutionary tracks. So like we do that work already. So like, so the rest of them is like interpolation, or it's still like very fast. Yeah. And if Jeff have like more comments, just please feel free to provide first.
Yeah, maybe I can just add a little bit of detail there. If you run a single binary in Mesa, it'll take somewhere between, I don't know, 1 to 20 hours. It could even take several days. Whereas a single binary in something like BSC, which is our sort of standard rapid population synthesis, can take something like 10 milliseconds. So any one binary is orders of magnitude more expensive. But because we've done this already and we've put interpolation functions on top of it, we're down to less than a second per binary now in our interpolation scheme.
Yeah, thank you. Okay, maybe we should move on to blue stragglers. The reason why I want Nathan will talk about a really cool blue straggler, but I first wanted to set him up by talking about this lower graph here in the slide. We talked on Friday and this morning about these post-AGB binaries, where you have an AGB donor, transfers mass to a main sequence accretor. Mass transfer is not conservative, so you lose mass out of the L2 point. You have to form the circumbinary disk. Then resees that post-AGB binary, makes it long-lived, but it's not going to live forever. Eventually, that post-AGB star will go across the AHR diagram, become a white dwarf, and you're left seeing the mass gainer, which we see as a blue straggler, because it's been rejuvenated by this mass, by gaining mass. Now, when you look at a cluster, look at the blue stragglers and look at their eccentricities and periods, you can see most of them are these moderately eccentric systems at 1,000 days, consistent with what we see for these post-AGB binaries. And so this was a Nature paper that came out more than a decade ago. But then there was this system here, and it didn't follow this trend. This system just drove me nuts. And now Nathan has figured out what it is. So take it away.
Oh, thanks, Max, and thanks for your confidence as well. So if you could just go back one slide, I just wanted to. So I'm gonna, but the last, I only have 4 slides or so, but the last slide of my talk, I kind of suggest some interesting, potentially interesting systems, if you believe the formation mechanism I'll talk about. But if anybody has observed anything like these systems, please email me at nlee@amnh.org. I would really appreciate it. I'd be really fascinated to read more about these objects. Okay, next slide. I can't actually do it. Thanks, Max. Right, so if the components of triples are all stars, then the outer tertiary can evolve eventually to overfill a Roche lobe. And there will exist, obviously, a large population of triples that can both overfill their Roche lobe while also maintaining dynamical stability. And so in this scenario, what can happen is you can accrete from the outer tertiary companion onto the inner binary, and the accretion can proceed via a circumbinary disk, as shown in the figure figure 1 there. And accretion from a CBD, as has already been discussed, can proceed by keeping the mass ratio close to unity. And so the question that we ask here is, could binary 7782, which has been observed in NGC 188, have been made this way? And so Robert Matthew and Aaron Geller observed this system in, well, a little before 2009, probably. And it has a period of order 10 days, an eccentricity of order 0.1, and the temperatures of both components are coincident, and so it's consistent with having a mass ratio of around 1. And if you don't mind going to the next slide, Max. And what you can do with this kind of system is actually kind of fun. So this shows the parameter space in the initial P out, P in plane, where P out is the period of the outer orbit of the triple, and P in is the period of the inner orbit of the triple. And this is the parameter space allowed for the hypothetical outer tertiary before Roche lobe overflow, assuming conservative mass transfer. And so the solid solid diagonal black line, this shows the period for the circularization radius, calculated assuming conservative conservation of angular momentum. So this is roughly where the mass transfer stream will end up, circularize, and then start to diffuse out due to viscous diffusion. The dashed diagonal black line shows a rough criterion for dynamical stability. The vertical dashed black lines show the maximum outer orbital period for which the outer tertiary would be Roche lobe overfilling, assuming an outer tertiary radius of 200 solar radii, which is the maximum stellar radius that will be reached on the AGB for the stars of massive interest here. And the horizontal dashed line shows the observed orbital period for binary 7782. And finally, the thick solid horizontal line, this shows the final allowed parameter space for the outer orbital period of the tertiary. And so to satisfy all of these constraints, this predicts twin Bruce stragglers in the inner binary with a mass ratio near unity. And it also predicts an outer tertiary white dwarf with an orbital period in the range of about 200 to 1,000 days. And so if anybody's interested in looking for that white dwarf, I would be very interested to hear if you can find it in the residuals. And I guess the next slide, if you don't mind, Max, quickly. So we can play the same game here, but relax the assumption of main sequence inner binaries and allow for white dwarfs as well. And so we consider a double white dwarf accreting from an outer tertiary via a circumbinary disk as one example in my paper with Sylvia Tunin, Simone Portuguese-Fort, and Rosalba Perna. And we consider a double white dwarf inner binary accreting from an outer tertiary via a circumbinary disk. And again, this plot shows the allowed parameter space for the outer tertiary before Roche lobe overflow. So the conclusion we reach is that the system must live within the blue triangle, so bounded by the diagonal black line, where the inner binary would be orbiting outside of the disk, the vertical black line, where the outer tertiary would not be Roche lobe filling, and one of the horizontal red lines, or the inner binary would rapidly merge due to gravitational wave emission and would not survive long enough to have a high enough probability of being observed. And so if you go to the last slide then, so it predicts something with a period in the range of the very similar range as we were seeing before, but a little bit shifted to the right. And so we can ask ourselves then, compact objects in the inner binary accretor will maintain a mass ratio of about unity. And if one companion ablates, the other companion is launched at the instantaneous orbital velocity and makes a hypervelocity object. So it raises the question, can we make some interesting exotic hypervelocity objects? So for example, hypervelocity white dwarfs near the Chandrasekhar mass limit, constraints on the maximum neutron star mass, and the production of hypervelocity millisecond pulsars. There's also a lot, our simulations, one thing we found in our simulations was that at low masses, in the masses characteristic of stellar triples, the evolution of the circumbinary disk tends to be very chaotic, presumably because there's just not enough mass in the inner binary for the CBD to orbit it in anything resembling an elliptical orbit. And so I just raised a bunch of questions about some of the mass transfer physics and some of these things. And that's it. Thanks.
Thank you, Nathan. So yeah, you have some nice questions there at the end. Does anybody have any answers or comments on those questions?
People are feeling sleepy. It's the end of the day.
Sleepy in the day.
I will take no offense.
I have a question. What is the efficiency of mass transfer from your tertiary to the inner binary?
Very low, very low. So I have a student whose project will be to systematically increase the mass of the inner binary and see if we can get up to a point where we actually start to produce a stable CBD and what that mass limit is. But yeah, we lose a lot of mass out of L2, as you said before. In our SPH simulations anyways. And I don't know what would happen with more sophisticated hydro simulations.
This question is not worth running for, but as someone who is radio pulsar timing adjacent, I'm actually curious about your prediction for hypervelocity millisecond pulsars. Has anyone found those? Do those exist? Or are you just saying that those could exist according to your models?
I'm saying they could exist. I would love. That's what I'm asking. That's what I'm saying is if somebody knows of a hypervelocity millisecond pulsar, please send me an email. I don't know of one, but I would imagine. But they should be detectable. So, I mean, I'm guessing they're not very common. So, given the sample from, for example, oh, his name has flown out of my head. The catalog of millisecond pulsars, but anyways, and globular clusters and everything.
Freire, maybe he did a lot.
Yes. Yeah, I'm not super surprised that of a sample size that large, you wouldn't have seen any such thing just yet, given the frequency of triples and all of the other aspect of parameter space.
I think the difficulty is that at 1,000 kilometers a second, you in lifetimes of 10 to the 10 years for the millisecond pulsars, you expect 1 in 10 to the 4 to be within a kiloparsec and observable, and we don't have 10 to the 4 of them by any means.
Yeah, okay. Exactly, yeah.
Do you have a question?
Yeah, so how long does the mass transfer phase last? Because I've thought a little bit with Rosanne DeStefano about looking for the signature of the accreting stellar mass binary. But I guess maybe, what do you think the prospects are, not for finding an outcome of this, but seeing this happen?
It's actually happening. Good question. I would defer to one of our binary evolution experts, and Sylvia or Selma or somebody else that I think has a better sense than I do of timescales. But these are lower mass objects, so I guess this is your best bet, right? If we're sticking towards main sequence stars and we're even happy to go towards, below a solar mass or so, then we're far better off than if we're at 10 solar masses. But more than that, yeah.
Selma is shaking her head, refusing to answer. Sorry, you can't see.
Okay. Sorry, Selma.
Okay. Well, thank you, Nathan. I put his 2 papers and a lot of these papers talking about mass transfer from a tertiary onto an interbinary on the discussions of the Slack channel. So please read and look there. The last evolved binary I wanted to make sure everybody saw was this beautiful light curve of a HW Virginis type eclipsing binary. What it is, it's a subdwarf B-type star. So this is the core of a giant star that has just emerged from common envelope evolution, and then a dwarf, M-dwarf companion. For common envelope evolution, I think we can confidently say that A dot is negative. These systems emerge at periods of a few hours. And so the hot star is so close to the cool M-dwarf that it's irradiating one side of that M-dwarf. So in addition to the eclipses, if it's edge on, you see these sinusoidal radiation reflection effects. Previous surveys have found, a couple hundred of these systems, and the ongoing test is finding even more of these HW Virginis type post-common envelope eclipsing binaries. So here's my question. What do large populations of these eclipsing binaries tell us about common envelope evolution? And I guess the second point I had is, how different is common envelope evolution from all the other kinds of migration we've been talking about? Can we use these post-common envelope binaries to benchmark simulations of circumbinary disk and gas, okay, aided migration? So I want to ask the theorists here, how different is common envelope versus other kinds of mass transfer? Okay, yeah. Go.
So I don't know the answer to your question, but I have a question here. What progenitor system are we talking about in terms of masses? How massive would the progenitor of the SDB star plus the DM star?
Yeah, so the subdwarf B star probably started off with a few solar masses. One to a few. I think they have a few massive counterparts of HW Virginis stars, but usually it's a M dwarf, low mass companion.
So when you're talking about common envelope, you're talking about a spherical pressure supported.
I'm talking about like a giant atmosphere that's very tenuous. The companion star is going through this tenuous envelope. You get dynamical friction where the companion focuses a wake, a high density wake behind it, leading to a net torque that causes it to in-spiral, going from separations of an AU, maybe a few AU, all the way down to 0.02 AU. So several orders of magnitude down in separation.
Yeah, well, this is very different than a prograde coplanar situation, because it's just, sorry. It's very different from the coplanar prograde binary situation where there's gap clearing by tidal resonances and all that going on. There are gas streams and all this stuff happening. So I would now, it might in some ways be closer to retrograde disks where there aren't these tidal clearings. The disk is rotating in the opposite sense of the binary, which has been studied. But I would say, given what most people have studied with circumbinary disks, that it is a very different physical situation. I don't think you can
two different
benchmark it with that. But that said, people have done extensive studies of common envelope systems where they're pressure supported envelopes that come about in very evolved systems like I was mentioning earlier today, where you have a red giant star with a close companion and red giant, envelopes, both of them, and then they orbit together. It's not a win, but you're inside, both stars are enveloped together inside a common extended envelope. And that is probably closer to what you're talking about. People have studied that. And, there's work I know by Ron Tam and other people on that kind of thing. And that would be closer, I think, to what you're talking about.
Tam did hydros in the 80s and 90s. I know Morgan McLeod and some others are doing it now. I'm just wondering if this group has talked to that common envelope group. Okay, just a thought. Another. Steve. Oh, yeah.
It's a question about slightly different angle. So if somebody wants to respond to this, they should go first. Maybe online.
Go ahead, Jeff.
Yeah, I'll just say, I think you asked the question, what can we do with these if we have large populations and how are they valuable? And if I got that question right, I think one of the most valuable things we can find from post-common envelope binaries is essentially the core masses. One of the things we don't know is when we lose the envelope, exactly how large is the core that's left over? Is there a little bit or a lot of hydrogen left over on the outside? And if you have large populations of this, combined with an orbital period, they can be very valuable to really come up with a better constraint on exactly where we define that core.
Similar, what do we know about the period distribution? So in the most simplistic way in which me and many others do common envelope evolution, you basically shrink this with an efficiency parameter, which I'm ashamed to do this way. But what happens there is that you basically can get outcome of common envelope evolution of all kind of different periods. There's not a very clear preference. If on the other side, in the common envelope, you get closer and closer to the core, and at the last moment, there might be some sort of Roche-lobe overflow happening inside this core, there may be funny effects for a binary system to say stall just outside the other core. And so what I'm hoping for is that the distribution of periods, if there's any sort of structure, it may tell us something about this last moment of the common envelope evolution. I don't know what's known there for these systems, but.
So yeah, they're all skewed towards very short periods. I think this is their typical example of a few hours, maybe going out to a day or so.
It's clearly also the selection effect. If after correcting,
even after correcting for probability of eclipses. The other thing though is we also see, these we see because of these irradiation effects. But we also know some subdwarf plus G-type stars, so more massive companions, and they're systematically a little bit wider separations, longer periods, or like a day to a few days, as opposed to all these M-dwarf companions, they emerge at less than a day. Okay, well, I have 10 minutes left here. As they do at my kids' kindergarten, let's just wake up and go. You can hear me? Can you hear me? Okay, thank you. So yeah, just changing topics here for just a little bit here, talking about binary star formation. And we got 3 slides here from Rajika.
Yeah.
Awesome.
Yes.
Take it away.
Yes, I'll try to be real quick. So I'm Rajika Karwida. I'm a postdoc at the University of Copenhagen. And I have been trying to investigate, I guess, the statistics of binary stars, multiple stars. In this figure, it's very messy, but this is, I run multiple cluster simulations in a 4 parsec cube box with different masses, and I look at all the bound systems that form. So in this plot, from low mass at the top down to higher mass on the bottom, I haven't been able to reproduce the final panel because the servers are down. I plot the separations of every system that forms. If you want to sort of understand, if you just take a slice, the x-axis is the star formation efficiency. You just take a slice through it, that is kind of equivalent to the histogram that Tobin was finding with the bimodal distribution. So I'm trying to see if I can compare my simulations to see if we can produce this bimodal distribution. I also investigate the formation pathways. So the markers indicate whether a system formed by a core fragmentation or dynamical capture, or this delayed dynamical capture that I defined. So if you can go to the next slide. Yes, so what I basically find is that for the lower mass simulation, which is a 1500 solar mass cloud, most of the stars are kind of formed through core fragmentation. So this delayed core fragmentation is when a sink is formed, it's technically unbound, but it later becomes bound to the sink that it's most bound to. So basically the blues and the purples are all core fragmentation, and the red is is dynamical capture. And I think in the lower mass simulations, we find that they are more clustered when I do 2-point correlation functions. So it seems like in the lower mass simulations, you get true core fragmentation, but when you get a higher masses, you get more dynamical capture systems. And go on to the next slide. So I've been trying to see if we can resolve this, the peak at 3000 AU. So this is just the histograms of the systems that form. And I mean, I'm still working on this. It's all very preliminary stuff, but like for the core fragmentation systems, we are sort of getting a peak initial separation in the few like thousands of AU. But, you know, as you saw in the first figure, that these systems, they evolve quite a lot, so they inspire a lot. So even though they might start out in a initial separation that we observe with the classier objects, they can in spiral and fall to different separations. So I'm still investigating this and trying to see whether the different formation pathways evolve differently as well. Yes, so I'll just leave it at that. And if you have any questions or you want to talk to me about this, please just message me on the Slack or email me.
Thank you. I have one question, but first, how about someone else? Caitlin, there we go.
Do I count as someone else?
Yes.
Okay, sorry, can you just say again, what is delayed core fragmentation versus core fragmentation? I just didn't catch that.
So this is, I guess, a purely theoretical thing that I've come up with. So in my simulation, I have sink particles forming that basically represent stars. And if there are if a sink forms and another sink forms and it is bound to the sink, then this is core fragmentation. But if say like you have this 2 binary here, a sink forms out here, but it's technically unbound, but later becomes bound to this system, then I call that delayed core fragmentation, because it does become bound to the star that's most bound to, despite being unbound.
Okay, so then what is capture? Dynamic, what is that?
Yeah, so these are scenarios where a sink is formed, and it becomes bound later to another star, but not with the ID. It doesn't have the same sink ID that it was of the star that was most bound to at birth. But I do have a schematic, but there are scenarios where it seems like a star forms and it's got other stars nearby that it can be marginally bound to, but then later on it becomes bound to a different star because of the way that it evolves.
Thanks.
Sorry, that was
yeah, thank you.
Yeah.
Thank you. And my question is, where are the short period, the closer binaries, less than a few hundred AU, are you not resolving that? Are you not finding core fragmentation curves on those scales?
Well, so the way that the simulations are set up, so we have a resolution of 50 AU, but the smoothing length of our sinks is a third of the cell. So we can resolve down to like 20 AU-ish. So the thing is, with the way the simulation is set up, we're trying not to resolve disk fragmentation and only look at like core fragmentation and other pathways just to see how the core fragmentation contributes to the multiplicity statistics of protostars.
Thank you.
So like some of my systems do evolve down to those closer separations.
Yeah. A question from John. You can go ahead.
Yeah, maybe I missed this. How long do your simulations run?
Depends on the mass. For the lowest mass, so I run them all until star formation efficiency of 5%. So the lowest mass simulation in total runs to about 27 million years, but the first sinks form at like 23 million years. So the stars are only really evolving for about 3 or 4 million years in the lowest mass simulation. In the higher mass simulations, the sinks don't get to evolve as much because it reaches 5% star formation efficiency quite quickly.
And then these ones that are captured, how tightly bound are they?
That's something I have to look at. They are actually bound. I just haven't looked at the degree of boundness, I guess. But that's maybe something I should look at.
Okay, thanks.
That's fair.
Great. Thank you. Oh no, is that John? Thank you for asking that question. Thank you, Rajika. So yeah, I just want to end with just 2 slides highlighting the takeaways from my discussion I had last week, since about half of you are here are new. When we talk about binary populations, we talk about binary star formation. Close binaries, less than 10 AU, cannot form in situ. You can't get core fragmentation. You can't get disk fragmentation at separations less than 10 AU. Yet when we look at tertiary stars are only a few million years old. We see that the observed closed binary fraction matches the field main sequence population. Okay, and so that's telling us that we had this fragmentation occur, disk or core fragmentation occur on scales larger than 50 AU, but then they migrated to these very short orbital periods on these very rapid time scales of 1 million years, maybe a couple million years, during that embedded class 01 protostellar phase. And there's other lines of reasoning that we think that these proto-binaries migrate inward. You can look at the excess fraction of twin binaries, which mass ratio is near unity. It declines from about 30% at 0.1 AU to maybe a couple percent about 1,000 AU. This idea is that the companion forms a wide separation of the disk, initially at extreme mass ratio, and then as it migrates inward, you have preferential accretion onto the secondary, driving the mass ratio toward unity. So the fact that we have this higher excess twin fraction at shorter periods, I think, is telling us that, again, A dot is negative. You have binary migration inward. And finally, this is just a toy model I discussed last week on the disk fragmentation or gas fragmentation and the migration of binaries in a disk. And the key takeaway is the driving parameter in the observed distribution of multiples was the mass of the protostellar disk or the mass in the gaseous envelope. If you have a more massive protostellar disk, you're more likely to have a massive star, an OB star. More gas means you're more likely to fragment, leading to a larger close binary fraction and a larger triple star fraction. I think this is why OB stars have a binary fraction of 90, 100%. 70% of OB stars are in triples. And also this, by having a more massive protostellar disk, you have a higher efficiency in the inward orbital migration. If you see solar type stars, the distributions peaks at tens of AU. But look at OB binaries, their orbital period distribution is skewed towards very short periods. Again, the idea is that you've had more efficient inward migration for these more massive binaries and more massive disks. So I just want to make sure everybody else got that story in a few minutes here. Any discussions about period distributions, mass ratio distributions, anything like that, and how that informs our knowledge of migration? Public.
I'll go first, sorry. I'm curious about the massive binaries part in particular regarding, I guess you're familiar with work from Maxwell Ramirez-Thanos.
Yes.
That more or less seems to show that there's mega year timescale evolution of the binary distribution of the binary periods in particular. So I don't know if this considers that more or less very long timescale process.
So yeah, I had a backup slide in case someone asked that. And so here's a summary of the observations very quickly. You have the Swan Nebula, M11, or M17. It's about 1 million years old. There are 60 early B stars in there. What they did is they found 11 of them that were young stellar objects, these massive stellar objects with a disk, or big VE stars. They looked at those 11 and found that none of them had close companions. And the binary fraction of those systems was 0. But we know from looking at slightly older clusters that the close binary fraction of massive stars is large, on the order of 70%. So one interpretation is that these close companions migrated inward between 1 million years, the age of the Swan, and these slightly older clusters, 3 million years, after most of that gas disk has dissipated. But I can't think of a model that can explain some kind of dynamical hardening that occurs between 1 and 3 million years without having some kind of sink to put the surrounding gas. And so the alternative explanation is the selection effect. We're picking the subset of OB stars with disks. They're biased against close binaries. Because we know by looking at tertiary stars that close binaries shorten the lifetime of the protostellar disks. And here's an example of the tertiary star sample where you can see that the disk fraction of tertiary stars, or close tertiary binaries, is less than that of single stars or wide binaries. So does anybody have an idea of how to get migration without a disk in 2 million years? Selma? You're asking for the microphone?
I'm just wondering about the numbers. So if 11 of those, you were all biased against finding binaries, then we should still have how many? Many more that do have binaries. And how many objects do you have in the system? Is that working out? Is the rest of the?
Yeah, so it's coming from the 60. So yeah, so that's a good prediction. I'm predicting that these the 49 early B stars that do not have this will actually have a close to 100% close binary fraction.
Well, that's a testable prediction, I presume.
to compensate for the deficit that we see in the ones with disks.
Is that's not measured, right?
Nope. Someone needs to do it.
Not me.
I've been telling you, you gotta do that. You gotta do that.
Very quick clarification. None of these 11 have close companions, but they have wider companions, or they have no companions
No, there's
at all?
no knowledge of companions. They just know that don't have any close ones.
They haven't ruled out wide companions.
Yeah. And probably that answer your question? Yeah, awesome.
Okay, I think this will close the session. Thank you very much.
Mm-hmm.
And just a quick announcement, thanks to all of the speakers today and everybody both in the room and online. I'll just once again reiterate, if you want to have discussions about things on the computer while in sessions, I strongly recommend Slack if you want to involve people in the room rather than Zoom. Dinner, I think, is starting at 6 p.m. And I will make sure that people check the doors for locked out people if you happen to leave the building in the next 30 minutes so that we'll let you back in. All right, thanks all for making it a great first day.